In the previous lection, I introduced the stoned estimation approach as a stepwise estimation consisting of at least 4 steps. And remember that the first step of the procedure was the convex regression, or CNLS. And this is really the engine of what drives the stone approach. So let us take a little bit more detailed look at the convex regression approach. So again, I remind you the taxonomy of the approaches. So now we look at this axiomatic estimation of the average curve. So in some sense, we are operating in the regression analysis setting similar to ordinary least squares, but now we do it in an axiomatic non-parametric setting. So let us now rephrase our model as follows. So we have our y, I do not call it anymore output, but it is just a dependent variable to highlight that we do not need to, of course, interpret this anymore in the production analysis setting, but it could be any context where we just have a dependent variable. We have some regression function f that satisfies certain shape constraints. So I here assume that f is monotonic increasing and globally concave, but it's possible to also impose some other type of shape restriction. It could be also concave instead of concave, and f could be monotonic decreasing, or we can relax monotonicity, or we can relax concavity, as we will see a little bit later. By x, I do not call them anymore inputs, but they are just explanatory variables. But of course, it's easy to then apply this technique to the context of production function later. And here I refer to epsilon as the symmetric error term, and I assume here that epsilon has 0 mean and constant variance, but as we saw in the previous lesson, it's also possible to then adjust this case to this average practice production function. And much of this material that I will use in the next slides is adopted from this book chapter in Handbook on DEA. So firstly, let me illustrate to you the conceptual definition of the convex regression problem. Suppose that we fit the regression function f to our observed data by minimizing the sum of squares of deviations, exactly like in the classic ordinary least squares estimator. However, in contrast to the parametric estimation, here we do not specify any particular functional form for the regression function f. So we only state that f is included in the set of monotonic increasing and concave functions. Notice that this is an infinite dimensional minimization problem, because there are infinitely many functions that satisfy these conditions that it's monotonic increasing and concave. So the set capital F subscript 2 is infinitely large. So therefore we cannot really use some brute force strategy of just trying different functions and trying to fit it to the data and select whatever fits the best. So in practice, this kind of formulation cannot be solved in any finite time. Of course, we could just try to enumerate different functions that satisfy these conditions and take the best, but in any finite time we cannot find the solution. So from the outset, it might seem like an impossible problem to solve. I should note also that there are some early studies like Clifford-Hildreth that I mentioned in this taxonomy from 1954 has solved this kind of problem in the case of the single regression case. So if this x is just a single explanatory variable, but in the multiple regression case, this problem turns out to be very hard to solve, and there are many incorrect solutions also in the literature. I get back to this in another lecture a little bit later. So In my 2008 article in the Econometrics journal, I developed the following kind of finite dimensional formulation, which can be actually solved by quadratic programming. So I set up this least squares problem as follows. So I will minimize the sum of squares of errors exactly like in the ordinary least squares regression, and we have certain constraints, little bit similar to the parametric programming approach that we considered in the parametric stream of literature. So although we operate in the fully non-parametric setting, I will parameterize the regression function using these coefficients alpha and beta, very similar to the linear regression analysis. So you can see the first constraint is actually just a linear regression equation. However, in contrast to the linear regression, notice now that this intercept alpha and slopes beta, they have subscript I. So this means that these parameters alpha and beta are not constant across all observations, but are specific to each observation. Okay, so this is a big difference to the linear regression here. Of course, if you just had this first constraint, then you could easily find if you could just take any arbitrary alphas and betas, you could just get the perfect fit, and the optimal solution would go to zero. So you could always have perfect fit to the data, but these other constraints are therefore very critical. Perhaps the last constraint is easy to understand. So we have this beta I must be greater than or equal to 0. So beta is vector and 0 is also vector. So all beta variable coefficients should be greater than or equal to 0. This is ensuring that the regression function is monotonic increasing. So this regression function cannot be downward sloping. And the second system of inequality constraints, so this is really the heart of the CNLS approach. So notice here that these inequality constraints, they keep this regressors xi, the vector xi is fixed. So in both left-hand side and right-hand side of the inequality, we have xi, same xi vector. However, we evaluate this xi vector with using these multipliers beta I and intercept alpha I. On the left-hand side of the inequality, we have alpha I and beta I, but notice that on the right-hand side of the inequality, we have alpha h and beta h, referring to some different unit, different observation h. And this is the key. We compare this regressors x using all different pairs of observations I and h, and this inequality must hold for every pair. So the inspiration for this kind of inequalities actually comes from the so-called Afriat inequalities or Afriat theorem. So in this extra materials for DEA, I discussed this 1972 paper of Sidney Afriat, and there is also other related work by Afriat that shows how to test for the well-behaved preferences and concavity of the preferences. So here I have taken some insights of Sidney Afriat and put them to a different context of regression analysis, which is not really directly straightforward step. So this type of optimization formulations have been also utilized before in the univariate case by Hildreth and many others. There's also related works by Banker and Mindirata that used a similar kind of Afriat inequalities in the context of frontier estimation. However, this specific formulation of convex non-parametric least squares goes back to my 2008 paper, and I find it quite intuitive that this formulation explicitly states these intercepts and slopes, these alphas and betas, similar to the linear regression model, which is nice. Another important contribution of my 2008 paper is I actually formally show that the optimal solution to this quadratic programming problem is equivalent to the optimal solution to the infinite dimensional problem in the observed data points xi. So I have stated it on the bottom part of this slide clearly. So this, if we denote the optimal solution to the infinite dimensional problem that I indicated on the previous slide, so the optimal regression function f asterisk, it is in fact equal to this optimal solution to this quadratic programming. So this, if we have this alphas and betas, so optimal alpha is alpha asterisk and optimal beta is beta asterisk, then this equation is always satisfied. In that sense, this quadratic programming formulation is completely equivalent to this infinite dimensional problem, and this can be solved by standard quadratic programming solvers and algorithms. So this can be actually solved. So let me illustrate this convex regression. Like I already indicated in the previous lecture, this convex regression is fitting a piecewise linear function to the data, but unlike DEA, it doesn't fit to the outer extreme, so it doesn't envelop all of the data points, but rather it fits the data to the middle of the cloud of points. But otherwise, the shape of the frontier is very similar to the DEA frontier. And I will show later that there is actually a connection to it. So you can also notice that this CNLS curve consists of a relatively small number of linear segments. And in this slide, I have indicated this kind of segments by red color. So notice that these supporting hyperplanes, these red lines, the slope of these supporting hyperplanes is decreasing as the x value is increasing. And in fact, these alpha and beta parameters, they characterize the intercepts and slopes of these red lines. And these inequality constraints in this CNLS formulation, they make this kind of comparison that, for example, when we take any given data point, then we are comparing the fit with all of these different red lines, and this optimization actually chooses then the best fitting curve for that particular segment. So these alphas and betas, they do not really characterize the function itself, but they characterize this kind of supporting hyperplanes. And because of the concavity of the frontier, when we get this kind of system of inequalities to characterize these fitted values. So that's how this parametrization works. So even though we have parameterized this supporting hyperplanes with these alphas and betas, it is still a non-parametric technique, because we are estimating actually this true but unknown f of x, and we characterize this solution with this kind of parametrization. But notice that it's wrong to interpret that we are assuming a piecewise linear structure. In fact, my representation theorem shows that if we try to fit any monotonic increasing and concave function to the data, the optimal solution is always a piecewise linear function. So in other words, I do not assume piecewise linear structure. It comes from the fact that the piecewise linear function is always optimal solution to this more general infinite dimensional problem. This is good to point out. So notice here that I have interpolated this CNLS curve as this minimum function. So if we take these supporting hyperplanes, I have systematically then chosen this lower envelope of these all these supporting hyperplanes. And the reason is the following. So previously in this, what I indicated, that this optimal solution to the quadratic programming problem is always the optimal solution to this infinite dimensional problem that we couldn't even solve. So this applies to this finite number of observed data points. So if we have a sample of n observed data points, then we have always a unique optimal solution to those given data points, unique in terms of the predicted value of y. However, recall that we started by estimating a regression function. So in that sense, we need to also interpolate somehow between these observed data points. And in my 2008 paper, I proposed to use this kind of minimum function that I have indicated here with this equation that is numbered as 7.5. So that refers to this book chapter that I referred to at the beginning. So a couple of points are worth noting for this, interpolation. So this minimum interpolation has actually a connection to data envelopment analysis. In fact, this minimum function, this f hat CNLS min, requires solving a linear programming problem, which can be actually interpreted as output-oriented multiplier formulation of DEA. In this case, we do not apply DEA directly to the raw data, but we apply DEA to the data of inputs X and our fitted values from CNLS. Okay, so this 7.5 is just the output-oriented multiplier DEA problem. So in this way, we can find the minimum interpolation for our data, and we can also show that indeed this minimum function is the lower bound for the optimal functions that solve this infinite dimensional problem that we started with. So in that sense, if we think about the minimum extrapolation principle of DEA, so in DEA it's also similar principle that we do not extrapolate beyond the observed data and what is the minimum set that is implied by the stated production assumptions. The idea of using this kind of minimum extrapolation is exactly the same here. It also strictly follows this Afriyat's 1972 approach of using the minimum function to estimate the production function. Of course, from the regression point of view, it's good to point out that using this kind of minimum interpolation can cause some bias in finite sample because of this. We use the minimum rather than maximum bound. A good thing about this minimum bound is that it also satisfies these shape constraints, monotonicity and concavity. We can also characterize the maximum bound, but it's easy to show that the maximum bound is not necessarily a concave function itself. So that's one reason also why we prefer to use the minimum bound to interpolate to the unobserved points. In any case, I want to emphasize that if our object of interest is the function, then this interpolation stage is necessary. It's not enough to just fit to some finite number of observed data points. We also need to characterize the entire function. So now, how does the CNLS regression relate to the DEA? So I already indicated in the case of this illustrative figure that DEA is a piecewise linear frontier function, whereas CNLS was a piecewise linear average function. So notice that if we impose additional sign constraints, so if we would restrict in our CNLS problem, think about this quadratic programming problem that I introduced before. So if we introduce a constraint that these deviations from this CNLS function must always be less than or equal to 0. Notice that this is similar kind of restriction that this classic Eigner and Chu parametric programming paper is also doing. So in some sense, if we do parametric programming version of convex non-parametric least squares and impose this kind of sign constraint, then we can be shown that this convex regression subject to this sign constraint gives exactly the same kind of piecewise linear frontier as DEA. So we have shown it in the operations research article with Andy Johnson in 2010 formally that this is always true, that if we impose the sign constraint for the CNLS problem, then we will get the variable returns to scale DEA frontier. So this really shows that not only the shape constraints or the axioms of convex regression are exactly the same as DEA. In fact, the DEA is just a sign constraint special case of the more general convex regression estimator. Of course, this result is only in the single output setting, but it can be also generalized to the more general multiple output setting using distance functions. And I come back to that point also a little bit later. So this also indicates that when we consider the stoned approach as this kind of stepwise estimation procedure, this result is very important for the internal consistency and the integrity of the method, in the sense that there is not any kind of information loss between these steps. So that's why convex regression is a very natural complement to DEA, because it's not only the same set of shape constraints, but also, in fact, DEA is a restricted special case of CNLS. So let us a little bit still extend the convex regression approach to also allow for proportionate error. So in the previous case, notice that we formulated the error term epsilon in an additive fashion. So we had dependent variable y was a function f of x plus some deviation. But actually, if you think about the stochastic frontier analysis, the composite error term is normally not specified like that. But I have here tried to capture the usual type of SFA specification, where in fact, for example, if you think about the Cobb-Douglas production function or the translog production function, in fact, we use the log transform model. So we should actually have a multiplicative error structure to get SFA as a special case. And this is indeed also possible in convex regression setting. And this development is something that goes back to my article in Journal Productivity Analysis in 2012 with Mika Kortelainen. So notice that if we take a natural logarithm of this kind of multiplicative error structure, then the log of output can be written as the sum of logarithm of the f of x plus error term epsilon. Now, important point to note here is that usually in the parametric estimation, in parametric specifications like Cobb-Douglas or translog, you can apply the log transformation directly to your inputs. So the standard procedure is to use logarithm of inputs. However, this is not really appropriate in order to maintain the shape constraints like concavity. So if you would apply just the CNLS to the log transform data, if you apply the additive formulation that we considered before to log transform data, then the resulting frontier can violate concavity. The appropriate formulation is stated on the bottom part of this slide. So we can still minimize the sum of squared of deviations, but now as the dependent variable we use the log of y, and then we introduce a new variable which I have indicated as Greek phi I. So phi I is also a model variable, and I have taken as a separate equation that phi I plus 1 is equal to the alpha I plus beta, vector product of beta I and xi. And we still have the system of inequality constraints, which I have referred to as Afriat inequalities, and we impose that, that these beta coefficients are greater than or equal to 0. The reason why I add phi I plus 1 is that with this trick, I avoid the situation that the computational algorithm is trying to take logarithm of 0, so potentially this phi I might be equal to 0, but I want to avoid that by adding there 1. But then I adjust this, so in fact phi I plus 1 is our fitted value of the frontier. And this way, by not taking logarithms directly from the x variables, but taking logarithms of the fitted value of output, we can model this multiplicative error structure, have this kind of logarithmic transformation without violating the concavity assumptions. So this kind of formulation, now we cannot estimate it anymore or we cannot solve this least squares problem by quadratic programming anymore, because we need to take this logarithm of variable phi. So this becomes a nonlinear programming NLP problem. It might seem that it's extremely difficult to solve as NLP, but notice that this nonlinear part only concerns the logarithm of these variables phi I, whereas most of the constraints remain linear inequalities or equalities. So in fact, this kind of problem can be quite efficiently solved by NLP, at least in the applications that I have experienced of this. This can be solved very fast with the NLP algorithms. Although in the NLP, of course, we cannot strictly guarantee that it's a global optimum in contrast to the Q-pair formulation. So some people prefer the quadratic programming formulation because the global optimum can be guaranteed, whereas then from the empirical point of view, this kind of multiplicative error structure can be very convenient, and there are a couple of reasons why it can be convenient. One is that if there is heteroscedasticity with respect to the size of the company, so if the error term tends to be larger for the large companies, then this kind of multiplicative specification can take care of that, because now this error term is proportionate to the size of the company rather than additive. Another reason is that if you want to impose constant returns to scale, then the multiplicative formulation is convenient because it can help to ensure that this regression line passes through the origin. So I have indicated on the bottom line of this slide that to impose constant returns to scale with multiplicative formulation, we can ensure that the value of function f with the zero vector of inputs is always 0. And by imposing constant returns to scale, this requires that we impose additional restriction on these intercepts alpha. So it's quite intuitive that if we impose that these intercepts alpha are equal to 0, like in the regression analysis, if we force the intercepts equal to 0, then this regression function must pass through the origin. But indeed, this also requires that we use the multiplicative specification. It is also possible to impose that these alphas are non-negative or non-positive, and these would refer to these cases of non-increasing returns to scale or non-decreasing returns to scale. So we have also possibility to relax concavity to complement these three classical cases. So we started with the variable returns to scale, I noted that we can do constant returns to scale, but we can also relax both concavity and constant returns to scale. And this is something that we have done in the eJOR article with Abulfaz Keshvari in 2012. So notice that we can, in advance, we can make this kind of dominance matrix indicated by capital P. So we can test that if the vector xj dominates vector xi. So if all elements of vector xj are greater than or equal to xi, we set this pij equal to 1 and 0 otherwise. So this pij indicates that if observation j dominates vector I in terms of this regressor's x, or in terms of inputs, if you like. So we can always enumerate this pij in advance from data. We can just, this is just a simple logical test. We could do it in Excel with just the if function. So having enumerated this pij, then we can just reformulate the convex regression problem as so that we multiply this concavity constraint by pij on the both hand side. So the idea here is that this concavity constraint holds whenever this concavity constraint holds between a pair of observations I and j whenever j dominates this observation I. But if that is not the case, then pij is 0 and this concavity constraint is relaxed. So this way this convex regression problem becomes actually so-called isotonic regression, or INLS. We refer to it as isotonic non-parametric least squares. And as it is illustrated in the article, the resulting regression function is actually a step function. And we also formally prove that the classic FDH approach is actually a sign-constrained special case of this INLS. So also if we here impose additional constraint that this epsilon I are always less than or equal to 0, then the resulting frontier is actually FDH. So I conclude that with this convex regression approach, it's very flexible also, that we can also relax concavity if we want. We can also impose different types of returns to scale assumptions. And my hypothesis is that also this INLS formulation can be extended to modeling, for example, quasi-concavity. But this requires some further work. So in the next lesson, then I will take these residuals from the convex regression or the related approaches as given, and then I proceed to decompose it. So I will move to this step 2 of the stone procedure.